In the first week of lecture, we talked about mechanical audio recording. At the very beginning, the phonautograph captured the vibration of sound on a piece of smoked paper. Later on, it advanced into using wax, hard rubber, and eventually polyvinyl chloride. Those recordings are analog. Sound is captured onto the medium continuously. These methods worked well, but suffer from a number of issues, particularly the unwanted introduction of noise when the medium is copied. It's like when you photocopy a picture, the image becomes more and more blurred when noise is introduced into the image in every copy. These issues can be overcome if the analog signal is converted into numbers, that is digitizing. Digitizing of sound means to convert the voltage changes into digital form that can be understood by a computer. The first step in digitizing an analog waveform is sampling. The continuous waveform of the signal are turned into numbers at regular intervals in time. In technical terms, we are converting an event that happens in continuous time into one that is chopped into slices of discrete time. During digitizing, the continuous waveform is quantized into discrete numbers. The more number of steps are used, the more accurate the digital representation can be. For example, this waveform is quantized into 17 steps. In digital audio, the resolution of quantization is called bit depth. A 1-bit word contains 2 steps, that is 0 and 1. A 2-bit word contains 4 steps. A 3-bit word contains 8 steps, etc. The standard bit depth that is used in CD is 16-bit. That is 2 to the power of 16, 65,536 steps. The number of discrete steps within a digital word limits the accuracy of the quantization process. The representative digital word can only be an approximation of the original analog signal level. What if the value falls between 2 points? In the quantization process, because we represent a whole range of sample levels by a single value, it results in an effective error in the representation of the true value. And this is known as quantization error. This error decreases with the increase in the number of quantization steps for the same range of sample values. In audio, the error resulting from quantization may also be treated as equivalent noise. That is the quantization noise. Quantization noise can be calculated by this equation, where n is the number of bits used to represent the level, so that 2 to the power n equals n, that is the number of steps. The number of samples taken in each second is the sampling rate. An analog signal must be sampled at least twice as fast as the bandwidth of the signal to accurately reconstruct the waveform, otherwise aliasing might occur. In this graph, the dotted line is the original analog signal to be captured, that is 500 Hz, captured by a 600 Hz sampling rate, the arrows. The solid line is the reconstructed waveform by the 13 samples. From this example, we can see that if the sampling rate is too low, the high frequency content creates a false lower frequency component, a 100 Hz sound. This is called aliasing. In order to prevent aliasing, the sampling rate to capture the highest audible frequency has to be higher than twice the frequency. Because the range of human hearing is 20,000 Hz, we assume the highest frequency we need to capture is 20,000 Hz. Therefore, 44,100 Hz is the standard sampling rate for CDs. But why not using an even higher sampling rate? That is because higher sampling rate requires more storage space. For example, for 1 second of sound, there are 44,100 pieces of data need to be stored. And each pieces of data is 16 bits, 705,600 bits. That is about 86 kilobytes. That was just 1 second. For 5 minutes of sound, it requires more than 25 megabytes. And this calculation is just for one channel audio.